the factors affecting compaction. We discussed previous one, the water content effect on compaction, then compaction energy. Now let's start discussion on the effect of type of soil on compaction. See, as soil nature changes or the soil grade changes, the compaction efforts or compaction of soil also changes. So first statement is, with change in type of soil, gamma D, that is dry unit weight, and OMC changes. Means if you consider an example of a sandy soil and clay soil, the maximum dry density obtained for both soil and OMC obtained for both soil are not the same values. Means OMC for clay soil is different and OMC for sandy soil is different. Dry density or dry unit weight attained by sandy soil and attained by clay soil are totally different. Clay with highest void ratio shows less compaction compared to the silty soil, and silty soil attain least compaction compared to sandy soil. Now why it is like this? Because they have more void ratio. What is meant by void ratio? Void ratio is ratio of volume of voids upon volume of solid. What is meant by volume of voids? Volume of voids is a combination of volume of air plus volume of water. Means by the process of compaction we are trying to remove the volume of air. When volume of air reduces, then void ratio, volume of void reduces. As volume of void reduces, void ratio reduces. Means for better compaction we have to minimize the void ratio. But as far as clay soil is concerned, it has initially highest values of void ratio. That's why under the same compaction energy or under the same compaction efforts, the compaction degree of compaction attained by clay soil is least compared to degree of compaction attained by a silty soil when we compare. Now if I am going to plot these two curves, that is compaction curve on a single graph, that is compaction curve for sandy soil and silty soil and compaction curve for clay soil. Look at the board. We'll take the graph. Here we have gamma D on y-axis and moisture content on x-axis. So first compaction curve is like this, which is having lower values of OMC and highest values of gamma D, and second curve may be like this, where OMC values are higher and gamma D values are lower. Okay, now question is, which curve is for clay soil and which curve is for silty soil? As I said, we are going to keep every terms constant for both type of soil. Means suppose we consider a standard Proctor test. We are going to perform compaction test, that is standard Proctor test, on two soils at the same time, and then we plot the curve. Now my question is, which curve is for clay soil and which curve is for silty soil? As I said, clay soil is having highest void ratio, means it contains large amount of volume of air, so it needs more time and more compaction energy to minimize the volume of air to attain higher compaction. But in case of silty soil, initially void ratio, that is void ratio is the least, that is volume of air is least. So under applied compaction energy, the soil shows higher degrees of compaction. So higher degrees of compaction means gamma D is highest. That's why this curve is for silt and this right side curve is for clay. Okay. So again, very important for 1 mark question in IES examination. They may provide the graph and here they mention X and Y, and the options are what is X and what is Y. Okay. So silt compaction curve obtained for silty soil is shifted to the left side of the graph, and compaction curve obtained for clay soil under same compaction energy shifted to the right side of the graph. Clay soil shows highest values of OMC compared to silty soil, and silty soil shows highest values of dry unit weight compared to clay soil. Now if we apply this same principle not only for the soil, for basic classification of soil, that is fine grain and coarse grain, then the behavior of soil remains same. Okay, look at the board. I'm going to plot the same graph, but this time graph is for water content on x-axis, gamma D on y-axis. Again, same curve, least value of OMC Another curve, highest value of OMC, least value of gamma D, highest value of gamma D. Now we are going to compare between fine grained soil and coarse grained soil. Previous one is a comparison of clay and silt. Now it's a comparison between coarse grain and fine grain. So which soil is having highest void ratio? That is fine grained soil compared to coarse grained soil. So highest is the void ratio, means highest is the amount of volume of air. So it needs more compaction energy to remove maximum amount of air to attain higher degree of compaction. Therefore, this curve is for coarse grained soil and this curve is for fine grained soil. Fine grained soil means what we learn from this? Fine grained soil will have highest values of OMC compared to coarse grained soil, and coarse grained soil will have highest values of dry unit weight compared to fine grained soil. Okay, so therefore from this graph, compaction curve for fine grained soil shifted to the right hand side, whereas compaction curve to the coarse grained soil shifted to the left hand side. One more important point is given in your note, that is you mark by different color pen. Pure sand does not have well-defined OMC. Okay, pure sand does not have well-defined OMC. How to represent this? And what is the meaning of this? When we plot a compaction curve for pure sandy soil, then curve behavior is like this, or the shape of compaction curve is like this. Means when we increase the compaction efforts, it attains the maximum dry density, and again with increase of water content, density decreases, but after some time again density increases. This happen only in pure sand, because sand do not have an electronic charges to keep the water molecule on the surface for the higher degree of compaction. Okay, so here curve is having somehow higher values of dry density, but they do not have fixed OMC. We can get OMC value here, we can also get OMC value here. So OMC is not well defined, it varies. Okay, therefore pure sand do not have well defined OMC. Fine grained soil shows less compaction than coarse grained soil. Clay with highest void ratio shows more compaction, least compaction compared to the soil with the coarse grained soil. Okay, so after this we are moving to the next concept, that is placement water content. What happen when we add water more than OMC or we add water less than OMC during actual execution of compaction process on site? Let's start discussion on placement water content. First, try to understand what is mean by placement water content. The actual amount of water added during field compaction process is called as placement water content. म्हणजे जे वॉटर आपण फील्ड वरती कॉम्पॅक्शनच्या प्रोसेस मध्ये ऍड करतो त्या वॉटरला म्हणायचं प्लेसमेंट वॉटर कंटेंट. अँड व्हॉट इज OMC? Optimum moisture content is the value obtained by conducting laboratory test on soil sample. So OMC is a laboratory value and placement water content is the actual value on field. Placement water content either more than OMC or less than OMC. Suppose when we conduct the laboratory test on a soil sample to be used for construction of an earthen dam, that laboratory test by using standard Proctor test gives me the value of say gamma D is equal to 2 gram per cc and OMC equal to say 20%. What is the meaning of this? The soil which we are going to use for construction of an earthen dam, if that soil contains compacted, if that soil compacted with water content 20%, then we can achieve highest values of dry unit weight for its strength. And when we are going to add water during actual execution, that time there are two possibilities. Whatever water we added during compaction, that water content is either less than OMC or sometimes its value is more than OMC. तो 20% पेक्षा कमी पण असू शकतो आणि 20% पेक्षा पण जास्त असू शकतो. जर water content on site exactly OMC इतका आला, then our compaction is very accurate, we are on right track, we will achieve the desired strength required on field also. Okay, so based on water content, soil remains on two states. The first one is dry of optimum and second one is wet of optimum. Means when placement water content is less than OMC, OMC ला जितकं पाहिजे असतं त्याच्यापेक्षा वॉटर कंटेंट जर कमी असेल then soil remains on dry of optimum. If water present during compaction is higher than OMC, then soil goes to wet of optimum. Now these two conditions we are trying to plot on a compaction curve. This is our compaction curve. Y-axis dry density or dry unit weight and x-axis percentage water content. The compaction curve is having the dotted line is indication of OMC as per laboratory results. If placement water content is less than OMC, I will mark the value over here, say 20%. If water content present on field, on site is less than 20%, say 15%, then soil remains on dry side, that is we call as dry of optimum. If water present in a soil on field is more than OMC, say 25%, then soil get liquefied, that we call as wet of optimum. Okay, so wet of optimum and dry of optimum are the two possibilities on field. Now both these are having special features. How they are useful and how they are achieved, we'll discuss step by step. So dry of optimum is a 1 mark question. You mark by different color pen and remember for a long time. Dry of optimum produces flocculated structure because there is attraction between the particles, because only some sort of moisture is present. But when moisture is excess than OMC, then structure get dispersed because of excess water and structure formed is dispersed structure. So dry of optimum having flocculated structure and the wet of optimum having dispersed structure. Okay, now which condition is going to offer more strength? Dry of optimum, when soil is get compacted with little bit water, it offers more strength. But when water is in excess quantity, then strength offer is less. Therefore again 1 mark question, dry of optimum condition provides more strength, wet of optimum condition provides less strength. What about pore pressure? What is meant by pore pressure? Pore pressure is exist only when there is a passage of fluid through the void spaces, and void spaces are more in case of an wet of optimum because there is more amount of water. Therefore wet of optimum shows higher values of pore pressure, whereas dry of optimum shows least values of pore pressure. Now in your notes all these points are given. The most important point is when strength is required with less compressibility, soil compacted to dry of optimum. आपल्याला ज्या वेळी फील्ड वरती सॉइलची स्ट्रेंथ हवी असते, then we always compact the soil by considering values of water content less than OMC, that is dry of optimum. And few examples are given. That examples are again very important for 1 mark question. Highway embankment, outer shells of earthen dam, subgrade where strength is important. Okay, look at the board. If I'm trying to draw the cross section of an earthen dam, which is suppose a trapezoidal in shape like this, on one side there is upstream side we have retention of water, downstream side there is a requirement of and stability because this water is going to create the pressure. So earthen dam is having two parts. The central part we called as core of dam, याला म्हणतात core of dam, and these inclined surfaces we called as outer shells. Outer shell. Okay, so whenever we want a strength, then we have to compact the soil to dry of optimum. So during construction of an earthen dam or construction of an earthen dam, the outer shells are compacted to dry of optimum. Same applicable for construction of an embankment. Now what is the benefit of compaction to wet of optimum? The points are given in your notes. When soil is compacted to water content more than OMC, then we call this as wet of optimum. It shows dispersed structure with less strength and more compressibility. या soilला परत compress करता येत नाही. It is highly compacted. That's why offer more strength. Therefore, dry of optimum offer more strength or with less compressibility, and weight of optimum offer less strength with higher compressibility. ही सॉइल अजून लूज असल्यामुळे आणखीन कॉम्प्रेस करता येऊ शकते. So offer more compressibility. To avoid, it's very important point you mark by different color pen. To avoid large expansion and swelling, the pressure soil is compacted to weight of optimum. म्हणजे ज्यावेळी आपल्याला swelling and expansion pressure कमी करायचं असतं, we are going to compact the soil to the weight of optimum. असं कुठं लागतं? In case of an earthen dam, at the time of construction of core of dam. What is core? It is made by special type of soil. This soil is totally avoiding swelling and shrinkage, because when water seeps through body of dam and when seepage is going to occur from upstream to downstream, when seepage reach the downstream phase, the stability of dam reduces. To control that seepage or to avoid the development of seepage path, this middle portion is constructed with such a soil which do not have swelling and shrinkage, and it resists the seepage path and also resists the development of pore pressure. So soil compacted to weight of optimum. Again, two examples are given: under pavement, floors and core of earthen dam. The flooring जे असतं ना, flooring where for construction of any paving blocks or normal flooring, the soil or sand placed below the flooring is compacted to weight of optimum. Okay, so examples are very very important. कोणत्या कंडिशनला dry of optimum and कोणत्या कंडिशनला weight of optimum. Okay, so here completes the concept of placement water content, which is either less than OMC or more than OMC. Now let's move to the one more important concept, that is special compaction equipments and their suitability. Let's start compaction equipment with their suitability. Suitability is very very important over here, because no one is going to ask the detailed procedure about the compaction, how compaction is carried out, how compaction is selected for a particular type of soil, how to measure degree of compaction. These questions they are not going to ask as a descriptive part. We have to focus on what type of equipments we use for the compaction and its applicability for a particular type of soil. Okay, so starting from first is a tampers. What is tamper? Tamper is a device which is connecting with a vertical rod and having heavy base at the bottom. This is we use for manual compaction. Why there is a need of tampers? The places where rollers cannot reach, for example corner places, corners or edges of abutment wall, their roller wheel cannot reach. In that cases the compaction is done by using tampers. Okay, so at a place where rollers cannot reach, that is confined area, trenches, corners of abutment, we use tampers. Second type of roller is a smooth wheel roller. Everybody knows smooth wheel roller is generally used for construction of an waterborne macadam roads, that is bituminous road. When bitumen is sprayed over the road surface, it is compacted by using smooth wheel roller. That roller is having heavy steel drums, one is at front and two heavy wheels at the rear side, at rear side, that is back side. And these wheels are designed with a particular load capacity. If you want to increase the load capacity of these both wheels, front and back side, we are going, either we can feel dry sand inside the drum or we can feel water inside the drum. By filling dry sand, its weight increases. As weight increases, compaction energy increases. As compaction energy increases, the degree of compaction increases. So most important sentence underlined by different color pen, it is used only for cohesion-less soil. When we are rolling a soil by using this smooth wheel, and if the soil is a clay soil that is cohesive, such a soil is going to stick to the surface of the wheel and compaction is not proper. That's why these rollers are applicable only for cohesion-less soil. It provides smooth surface at the end of day's work. As I said, during construction of bituminous road, when roller rolls over the surface of bitumen aggregates, at the end of work we will find it's a smooth surface. Okay, so again it is used to provide drainage passage. Whenever there is a problem of a ponding situation, to provide the cross slope to the road surface, that is to make the or to create the chambers, we used the smooth wheel rollers. Okay, now number 3 is pneumatic tire roller. Pneumatic word comes because of it's a pressure, and tire means we are going to use rubber tire instead of a steel drum. In smooth wheel roller we have steel drums, but in case of pneumatic roller we have tires, and tires are used in multiple numbers. The number of tires and the tire pressure depends upon the achievement of degree of compaction. When we want higher degree of compaction, then pressure in tire increases. If we want lower degree of compaction, then pressure we reduces. Means pressure is adjustable, number of tires are also adjustable. Tires are designed in such a way, the front two tires are moving in forward direction, the gap between the two tires is covered by the tire located at the back side. Similarly, when these two tires moving in a forward direction, the gap between these two tires is covered by the tires at the rear side or back side. Based on this technique, we are going to compact the soil. As rubber tire is used, that's why this roller is applicable to both type of soil. You mark this sentence by different color pen. Pneumatic tire roller is applicable for both type of soil, that is cohesive and cohesionless. Tire pressure is used to compact the soil, means again we are going to adjust the pressure based upon the degree of compaction. It is applicable for both type of soil, that is cohesive and cohesionless, and tires are varying in size based upon the nature of the work. Okay, after this we are moving to the next roller, that is sheep foot roller. Under the heading of types of roller and their suitability, the next important type of roller is sheep foot type roller. Why this roller we call as a sheep foot type roller? Because the steel drum which is available on a front side, that steel drum is mounted with the stud. The studs are also made up of steel. Look at the board, here is a cross section of that steel drum. These are the studs located on a surface of a steel drum. These studs are arranged in such a way, the space between two studs is covered by the studs arranged in the second row. The space vacant in between two studs is covered by the studs available in the next row. Means it's a staggered arrangement of the studs, and the studs are going to compact the soil by using a action of known as a kneading action. Kneading action means it is a slowly application of pressure on a same point with repetitions, and when a constant pressure is applied at the same point with a number of repetitions, then soil is going to get compacted with high degree of compaction. So you make this underline by different color pen. Sheep foot roller works with principle of a kneading action, and as the studs are mounted over there, there is no question of sticking of soil to the surface. So this roller is mostly used for cohesive soil, especially compaction of clay. This roller is not suitable for cohesionless soil. It is only for cohesive soil, sheep foot roller. The next type of roller is vibratory type of rollers. Means a principle of vibration is involved in the process of compaction. This roller is similar to roller which we use in a cohesionless soil, that is smooth wheel roller, to obtain a smooth surface at the end of day's work. But here the difference is the front drum of roller is having vibration mechanism. When roller starts operation, the front drum is going to produce vibration, due to which soil receives the pressure from this drum as well as the action of vibration. So compaction we can achieve at the highest level. But remember, this vibratory roller is applicable only for cohesionless soil, especially sandy soil. In case when there is a presence of sandy soil everywhere, even we excavate far depth below, we will find the sandy nature of soil. In that case, the foundation is constructed by using vibroflotation technique, and vibrofloat works with principle of vibration. The same principle is in the roller, but vibrofloat goes deep inside to construct the foundation, but roller is going to provide the smooth surface or compact the soil on upper surface by introducing vibrations. So front drum vibrates and rear drums is going to apply the pressure. Okay, so again, if you want to increase the weight or pressure of the roller, feel the ballast or water inside the drum, or you can use dry sand inside the drum. When we see, if you want to increase the load, feel extra material inside the drum, because these drums are having provision to feel or to load some extra material inside the drum. Okay, the next type of roller is mesh type of roller. Mesh type of roller is very similar to a network of a steel mesh. Means the front drum is designed with mesh. It is hollow section, open mesh is there, and this roller is specially used for compaction of a coarse grained particles, especially gravels and cobbles, because it is mesh opening is not fine, it is having a large size. That's why for placing the stone particles or over a ground surface, a mesh type of roller is used, and it is practicable only for a large size particles, not for cohesive soils. Okay, so again, the compaction pressure is applied by using front wheel, and rear wheel is again made up of the solid section made up by material steel. After this, we are moving to the one more important roller, but that is not a roller, that is again a vibratory compactor. Just like a vibrator we use for compaction of concrete, same type of handy vibrators are also used to compact the soil, and these vibrators are used for those places where roller cannot reach. Okay, so here completes the all types of rollers and their suitability. Again, important is the name of the roller and its function with their suitability for a specific type of soil. Let's move to the next concept, that is relative compactness or degree of compaction on field. Relative compactness or degree of compaction is used to verify the achievement of compaction on field. It is very simple, because when we are going to conduct a compaction on field, before that we have results of compaction of soil in the laboratory by using either standard Proctor test or modified Proctor test. Suppose if I use a standard Proctor test and this gives me the value of dry unit weight, say 2 gram per cc, and OMC is equal to say 35%. When a soil tested in the laboratory, it gives me the dry unit weight 2 gram per cc according to standard Proctor test. Now the same soil, when used in field for construction of the designed structure, it is either embankment or earthen dam, whatever is there, the structure made up of soil, when soil is placed on field and it is compacted by using mechanical equipment, say roller, then after rolling process, soil should have attained the desired value of compaction, and that value we are going to check on field. Suppose on field I am going to record the value of dry unit weight. Suppose I got this value 1.8 gram per cc, like this. When tested in the laboratory, 2 gram per cc, on field 1.8 gram per cc. Now how to check whether we attain the compaction or not, or how to obtain relative compactness? So for that, the formula is very simple. Degree of compaction or relative compactness is equal to, it's a ratio of dry unit weight of soil on field divided by dry unit weight of soil in laboratory multiplied by 100. Dry unit weight of soil on field and dry unit weight of soil tested in the laboratory multiplied by 100 as it is expressed in the percentage. Suppose we'll use these values in this expression. So gamma D value is 1.8 on field divided by the value in the laboratory is 2 multiplied by 100. When we solve this, our answer comes less than 100%, means we are unable to reach the compaction level up to 100%. Means we need to increase further compaction process. So this is a technique to calculate the relative compactness or degree of compaction. Okay, after this, let's move to the next important concept, that is field compaction control. Means how to evaluate the values of dry unit weight and water content on site for a selected soil for the construction of any earthen work. Let's start discussion on field compaction control. Field compaction control, in simple words, it is the technique to verify the compaction achievement on field. Because when soil sample is tested in laboratory, we got the good results. Whether the same results we are getting on field or not, that verification we call as the field compaction control. It means there is establishment of a relationship between laboratory results and the field results. Suppose laboratory results by using standard Proctor test gives me the value of dry unit weight 2 gram per cc. Whether when soil is compacted on field in reality, then it is possible to achieve that dry unit weight is yes or not. If it is yes, then it is called as good compaction. If not, then we are lagging by some compaction process. That verification and establishment of relationship we call as placement water, we call as field compaction control. It gives me the value of relative compactness. In our previous concept we learned this. Relative compactness means what? It is the ratio of dry unit weight of soil on field to the dry unit weight of soil in laboratory. That ratio we can find out, that is called relative compactness. Okay, if relative compactness very close to 100% means our compaction efforts on field are good. If not, then we need to modify. Initially, in this case we are going to calculate water content and dry unit weight, because standard Proctor test gives us two results: maximum dry density and OMC, optimum moisture content. These two things we are going to calculate on field, that is water content and dry unit weight. How to calculate water content on field? Because we don't have enough time to wait for a results. Oven drying method for finding the water content needs 24 hours. We want results in a shortest time, and for shortest time with accuracy we have two methods. The first one is water content determination by using calcium carbide method, that is hydrometer method or moisture meter method, and the second one is by using Proctor needle method. Generally we prefer Proctor needle method. So what is Proctor needle method? Look at the board. A sketch of Proctor needle is drawn on board. It has handle at the top, then sliding ring which is used for the recording the penetration resistance, then vertical shaft, then here is we have needle shank. At the bottom of needle shank we are going to place the needle. Needle shape and needle size changes according to the change of type of soil. Okay, so how this compact equipment is going to help us to find out the water content? That is by using penetration resistance. You mark this point by different color pen. Proctor needle works with principle of resistance, means how much is the resistance offered by the soil against the penetration, that provide me the value of water content. Now look at the board, how it works. That is very, very important for us. So for its working we need a compaction curve, and we know that compaction curve is the laboratory result. So for a compaction curve, on x-axis we have percentage water content, on y-axis we have dry unit weight. Say percentage water content we decide, say 10%, 20%, 30%, 40% and say 50%. These are our examples, trials. So for this water content, suppose we know that dry unit weight value goes on increasing with increase in water content, it attains highest value, and then with increase in further water content the value goes on decreasing like this. So these are our points: 1, 2, 3, 4 and 5. Let us join these points by a smooth curve. This is my compaction curve. Now how this Proctor needle works? In laboratory, based on the nature of soil sample we decide the size of needle or the type of needle, and this equipment is available in the laboratory, and that equipment we are going to use to find out penetration number for every trial. How many trials we have here? Here we have 5 numbers of trial. First trial when water content is 10%, second trial 20%, 30%, 40%, 50%. From this graph one can see this value is nothing but OMC, and this value is MDD, maximum dry density. Now while plotting this graph, we are going to plot a calibration curve for Proctor's needle. How to find this calibration curve? In standard Proctor test, we have a standard capacity mold. This mold we are going to fill in 3 layers of soil. Every layer is compacted with 25 number of blows, and after completion of third layer with 25 number of blows compaction, we are going to measure the mass of that Proctor's mold, and that mass and volume we use to calculate bulk unit weight, and by using water content we can find out the dry unit weight. Now when the mold is ready to take its mass, we are going to hold the Proctor's needle inside the mold, and inside the mold needle is hold, and we are applying a compressive pressure, and we have to penetrate this needle by a distance of 7.5 centimeter. Inside this mold we are going to penetrate, means we are applying pressure from top such that penetration should be 7.5 centimeter inside the mold. When needle penetrates inside the soil, it's showing the resistance offered by the soil, and that resistance we are going to record by using sliding rings, and this resistance we are going to keep record for every trial. Means for first 10% water, for first trial with water content 10%, we are going to have a record of penetration resistance. Then for second trial with water content 20%, when mold is ready, again insert the Proctor's needle, apply pressure from the top, and measure the resistance required for a penetration of 7.5 centimeter value, and keep the record of every resistance for all the trials. And we know that initially when water content is less, resistance offered by the soil is more. With increase in water content, resistance continuously goes on decreasing, and these values I am going to plot in the same curve. Look at the board. Here we'll extend like this, say 5, 10, 15, 20, 25, 30 and so on. So for first trial, this is what is written on this vertical axis. This is for penetration resistance. This is penetration resistance. Suppose for first trial when water content is less, I said resistance offered is higher. So with same on the same vertical line, resistance is higher, say 30. Mark this point. For second trial, as water content decreases, water content increases, resistance offered by the soil decreases. So for 20, say resistance is 25. So here we get the value 25 on this axis like this. 25. Here is resistance. Third, water content 30% for third trial. Say resistance is 15. So on this axis mark 15 like this. Reference is from this right side 15. Water content is 30%. For fourth trial, say number of resistance is 10. Mark over here. Then last one suppose is 5. Now we got all these points. These points we have to join by a smooth parabolic line like this. And this line we call as calibration curve. Calibration curve. By considering the same needle we are going to use in field, the same needle is used in the laboratory. Now setup is laboratory work is done. Now let's move to the field compaction. When field compaction process is going on and we want to verify what is the value of water content right now, in that case take the same needle, and that needle we are going to use to apply the compressive pressure, and penetration resistance is recorded. Now let's see how to calculate the value of field water content by recording the penetration resistance offered by the soil for a penetration needle. Look at the board. We have a compaction curve with calibration curve also. Now this needle I am going to hold on a compacted layer of the soil. Suppose this layer is compacted. Over this surface I am going to hold this Proctor's needle and I am applying the pressure from the top such that the penetration is about 7.5 centimeter. Okay, when needle goes 7.5 centimeter penetration, we stop application of pressure and we measure the resistance by using sliding ring. And that resistance value we are going to use to find out the water content. Suppose example, that resistance value is say 28. So we have graph over here. From that graph, take the value 28. Suppose the value is 28 over here. From this position of 28, I am going to extend the line up to the calibration curve. Look at the board. Continuously increases. And this horizontal line from number of penetration resistance 28 is going to touch the calibration curve at one particular point. From that point, take vertical line exactly 90 degree, and this vertical line is going to cut the horizontal axis at one particular point, and this point is not gives me the value of what? Water content. So water content value is available by using calibration curve. This is the way or technique to obtain the values of field water content by using Proctor's needle. So very important point is penetration is 7.5 centimeter. Needle changes with change in type of soil. First calibration curve is developed by taking the readings in the laboratory, and then with the use of the same compaction curve and calibration curve we can find out the water content on field by measuring the penetration resistance. Now next part is how to calculate the unit weights, because in unit weight in laboratory we have weight upon volume. So what technique we can use to find out the values of unit weights? Let's discuss as a last part of this field compaction control. Determination of dry unit weight of soil, which is essential for defining the field compaction control. In the previous part of field compaction control, we learned how to calculate the values of water content by using Proctor needles and calcium carbide method. Now we want a dry unit weight to compare with the laboratory results by standard Proctor test. There are two methods available to find out the dry unit weight. The first one is a core cutter method and second one is a sand replacement method. Remember, these two methods will never provide the value of dry unit weight directly. To obtain the dry unit weight, we require a relationship between bulk unit weight and dry unit weight, because these two methods gives the value of bulk unit weight, not the dry unit weight. So what is the relationship there? Dry unit weight is equal to bulk unit weight upon 1 plus water content. Water content is already available with us either by Proctor's needle or by calcium carbide method. Now it's time to find out the bulk unit weight. Okay, so let's start with the first method, core cutter method. In core cutter method, we require a cutter whose internal diameter is D, height is H, and we require a rammer of weight approximately 3 to 4 kg. The purpose of rammer is to apply compaction energy on the top of the cutter to avoid the breakage or to avoid the direct impact of rammer on the surface of cutter. We provide a dolly. Dolly is provided to sustain the impact from rammer. Now cutter is placed over the ground surface. First clean the ground surface, remove all the dry leaves of the plants, remove some bushes, remove some dust particles and make the surface clean. Put the core cutter over the compacted surface, because we are testing on field. Whatever compaction is done by using roller, first clean some portion of that surface, put the core cutter, and then by using rammer apply continuously the blows over the top of the rammer. Okay, means by using rammer apply blows over the top of the cutter. Now due to compaction energy, the cutter moves inside the ground. Now take the cutter out, clean the top portion, remove the excess soil connected to the surface of the cutter, also at the top of the cutter, remove the dolly and make the soil surface exactly parallel to the top of the cutter. Now we have empty mass of cutter. Now note down the mass of cutter with compacted soil. From that, subtract the mass of empty core cutter. Means look at the board. If I said M1 is empty mass of cutter and M2 is mass of cutter plus compacted soil. So from that I want mass of compacted soil. M3 is equal to M2 minus M1. Now I got mass of compacted soil. Now I need a volume to find out the unit weight. So for volume, simply use volume of cutter. Volume of cutter is equal to area of cutter pi by 4 diameter square multiply by height of cutter h. Internal diameter we can measure by using vernier caliper and height by using scale. Now we have volume, we have mass, then find out bulk unit weight is equal to weight upon volume, or can say density is equal to mass upon volume. Once we get the bulk density or bulk unit weight, find out the value of dry unit weight by using gamma upon 1 plus water content. So this is the technique to find out the dry unit weight on field. Now we have value of dry unit weight, we have value of water content. Now compare these values with the laboratory results. If value obtained on field for gamma D is approximately close or equal to the value of dry unit weight obtained in laboratory, then we can say the compaction efforts are 100% or relative compactness is very close to 100%. Okay, here completes core cutter method for determination of bulk unit weight and the dry unit weight. Now let's move to the second method for calculation of unit weight on field, that is sand replacement method. Let's start discussion on a sand replacement method. This method is used to find out the bulk unit weight and the dry unit weight of a soil on field. And by knowing the values of dry unit weight, one can find out the value of relative compactness or degree of compactness essential for decision of the compaction level on field. In sand replacement method, we require a dry sand passing 600 micron sieve and retained on a 300 micron sieve. In sand replacement method, basically we have three apparatus. The first one is a sand pouring cylinder, second one is a calibration tin, and third is a metal tray. Metal tray is having central hole. The diameter of central hole is exactly equal to the diameter of calibration tin. Sand pouring cylinder is having conical shape at the bottom and sand is filled in upper portion, and to release the sand in a downward direction there is hole available, and release or the movement of sand is controlled by using shutter. Means when shutter is closed, movement of sand is completely restricted. When shutter is released or opened, sand moves in a downward direction. The procedure is very simple. First of all, we are going to calculate the bulk unit weight of sand, not the soil, in laboratory or on field. So what is the technique here? Look at the board. First of all, I am going to record the mass of calibration cylinder, mass of pouring cylinder, mass of pouring cylinder with full fill up of sand. I denote this value as M1. Means a dry sand I am going to fill inside the pouring cylinder up to its top level, say 1 centimeter or 2 centimeter just below the top portion sand is filled and its mass is noted down. Then this pouring cylinder is kept on a glass surface or a smooth surface, that is called uniform surface without undulation, and shutter is released. When shutter is released, sand moves in a downward direction, and when it moves continuously, the sand is going to occupy the volume of a conical shape, and when movement of sand is completely stops, then we are going to close the shutter. Then you will find out the sand is going to acquire this type of shape on the surface like this. Now when there is no movement of sand observed in the top portion, take the pouring cylinder and again put on weighing machine and note down the mass of that cylinder that we call as M2. So this will get mass of pouring cylinder after release of sun. Now this mass is without mass of conical portion, means mass of sand occupied the conical portion. Means now if I want the only mass of conical portion, I will do the subtraction of m2 and m1. So I will take m3 as mass of sand in a conical portion. Then it gives me by doing m1 minus m2. Okay, m1 initial mass minus mass of cylinder available after pouring the sand into conical shape. Then m1 minus m2 gives me the value of what? Mass of sand in conical portion. Okay, now after this, let's move to calculation of bulk unit weight of sand by using calibration tin. Now again, the sand is filled in a pouring cylinder. Whatever sand we collect on that glass surface, the same sand again fill up in the pouring cylinder and its mass is recorded again. Now take this calibration tin. Its internal diameter is measured by using vernier. Height is measured again by using vernier or scale. Then calculate the volume of calibration tin. Volume of calibration tin is equal to pi by 4 d square. This is diameter, d square, and height is h into h. Say this volume will get in centimeter cube converted to meter cube. Okay, now volume is available. Now I am going to pour the sand in a calibration tin. Now calibration tin is hold like this. Suppose it's the calibration tin, and the pouring cylinder I am going to kept over this calibration tin. Pouring cylinder is now hold exactly over the calibration tin, and sand is released, means shutter is open, sand starts movement in a downward direction. Slowly the sand is going to occupy the volume inside the calibration tin with formation of conical portion at the top like this. Now I am interested to know what is the mass of soil inside the calibration tin. So for that I am going to take the empty mass of this calibration tin before conduction of this process of movement of sand inside the calibration tin. So I will do this. M4 is equal to empty mass of calibration tin. Okay, I will take this M5 again, mass of tin plus poured sand. Okay, means M5 represents what? Mass of this calibration tin plus sand fill up inside this calibration tin along with the conical portion. Okay, now I want the mass of sand inside the calibration tin. So for that I will do M6. M6 is equal to mass of sand inside calibration tin. How to do this? I want only this mass inside this calibration tin. So for that I will take M5. What is M5? Mass of tin plus poured sand. Then I need to subtract this mass, that is minus, and what is this mass of that conical portion? M3. So M5 minus M3 means M5 is the mass of calibration cylinder plus this conical portion. From that M5 I am going to subtract M4 first. M4 is the empty mass of this calibration tin minus M3. One more time, listen carefully. M5 represents mass of tin with the poured sand inside as well as in the conical portion. From that subtract the empty mass of tin and then again subtract mass of this conical portion sand. You will get mass of sand only inside the calibration tin. Now mass of sand is available, volume of calibration tin is available. One can calculate the value of bulk unit weight of sand is equal to mass of sand divided by volume of sand, like this. So volume is volume of calibration cylinder pi, this is pi by 4 d square into h. So volume is known, mass is known, it is m6. So we can write m6 divided by v, you will get this density kg per say meter cube, like this. Now we got the bulk unit weight of sand, not the soil. Now let's see how to use this technique on field to get the value of bulk unit weight of soil, that is on field. Look at the board. Now we are going to discuss how to use this sand replacement application to find out the bulk unit weight of soil on field. Now when we start discussion on this, we got the value of bulk unit weight of sand is equal to weight upon volume, that is in kg per meter cube. This value is available with us. Now select the compacted surface where compaction process is going on. The portion where you want to know the value of bulk unit weight, exactly over that portion place the metal tray. As I said, metal tray is having central hole. When you kept the tray exactly over the compacted area or compacted field, start dredging of soil mass within that hole itself, and whatever sample we extract, all the sample we have to collect in a same tray. The sample we have to collect in a tray. The depth of hole approximately equal to height of calibration tin, approximately. Okay, now when hole is made, we are going to remove this tin. Metal plate is now removed, and exactly over this we are going to place the pouring sand cylinder, like this. The initial mass of this pouring cylinder is recorded. Okay, say m1 is equal to initial mass of pouring cylinder. You can take any mass, there is no restriction that how much mass I have to keep. You can put any mass of a sand inside the pouring cylinder. Now that cylinder of known mass is kept exactly over the excavated hole and release the shutter. The sand starts its movement in a downward direction. The sand goes inside the hole made inside the ground. After when we realize the movement of sand completely stops, then take the pouring cylinder out. After taking pouring cylinder out, you will find the shape of sand filling like this. It's a filling of sand. Now I am interested to know how much is sand is inside this portion of hole. या hole मध्ये किती sand आहे मला हे काढायचं आहे. So after removing the pouring cylinder, I am going to note down the mass of the pouring cylinder after pouring. So say m2 is equal to mass of pouring cylinder after releasing of sand. Now I want to know what is the mass of sand inside this hole. So m3 is equal to, how to get this mass? m2 minus m1. When I do this, I will get the mass of sand total, means inside the hole and in a conical shape. So m3 is equal to m2 minus m1. But if you remember, in our early stage of this explanation process, we calculated the mass of sand in a conical portion, that is minus mass of sand in a conical portion. When we do like this, then we'll get the mass of sand exactly inside the hole. Now mass of sand is known, bulk unit weight of sand is known. We can find out the volume of the hole. See, we cannot measure the volume of hole by using vernier caliber or scale. Its shape is non-uniform. That's why to calculate its volume, we use the bulk unit weight of sand. Okay, now m3 is available, that is m2. Sorry, here is m1 minus m2. Sorry, make a correction over here. m1 is the initial mass minus m2. m2 is the mass after pouring. We'll get the mass of sand in the hole plus conical. Minus conical, we will get the value of mass of sand within the hole. Okay, now I will use this technique. Bulk unit weight of sand is equal to mass of sand in a hole divided by volume. So gamma sand is known to us in kg per meter cube. Mass of sand m3 is known. You can get the value of what? Volume. तर मला होलचा व्हॉल्यूम मिळाला. Now I'm going to calculate the bulk unit weight of soil. So gamma of soil is equal to mass of soil divided by its volume, divided by volume of soil. Now whatever soil sample we collected inside the tray at the time of excavation of a hole, all that soil sample we are going to kept on weighing machine to note down its mass, that is mass of soil, and volume is available over here because this value is known, this value is known. We can find the value of what? Volume. When we replace volume over here, we'll get what? Bulk unit weight of soil. It's okay. Now again, by using either moisture meter method, that is calcium carbide, or by using standard that is Proctor's needle method, we have the value of water content. Therefore gamma D dry unit weight is equal to bulk unit weight of soil divided by 1 plus water content. We'll get the value of what? Dry unit weight on field. Okay, so this is the procedure for finding the bulk unit weight and the dry unit weight of a soil by using a technique of a sand replacement method. Okay, here completes the sand replacement method as well as all the concepts from compaction of a soil. Now as far as problem part is concerned, we have very less number of problems in case of compaction, but theoretical part and important terms involved maximum in compaction. So you practice the questions from your online app as well as from previous gate, and as well as the questions from given booklet. Okay, so here completes the compaction chapter. I would like to say thank you very much for listening and watching this video carefully, and after this we are moving to the most important chapter, that is consolidation. So thank you very much. Thank you.